Hello, more questions now on forces on the slope, exercise 21C.2. We've seen exercise 21C before, but I want to look now at a specific part of this, which deals with, well, forces on the slope cause problems, you see. So I definitely just go through this and perhaps spend a bit more time on it. So a little starter for us. Now, it does say, look, resolve the forces W. Well, obviously the W refers to the weight going straight into the hill. Now, we all often resolve this going this way, which it would be called parallel to the slope, and this way, which would be called perpendicular to the slope. Yeah, if need be, just pause the video just briefly if you can't remember. Go back and look at your notes and see what they are. If you've done that, hopefully you remember that when you resolve this weight parallel to the slope, you get W sine theta. You might write that as mg sine theta. And in this case, of course, theta is obviously 30. And this way is mg cos theta, or 30 in this case, I suppose. Let's put 30 there. Or W cos 30 if you prefer. Notice again, sine theta parallel, cos theta into the slope. I've got three examples for you on this. So we've got a rough inclined plane. The rough, of course, implies there's friction. Inclined, it's on the slope. So I'm going to draw it. There it is. Not the best picture in the world, but you get over an angle theta. A particle of P, there it is. There's my particle of mass M, lies at rest on the slope. Now, by definition, it's trying to fall down the hill, and down the hill is mg sine theta, and up the hill then is F, the friction. Given that P is on the point of slipping, well, that basically means these two things are equal. So F equals mg sine theta. Mg is sine theta. Find in terms of theta the coefficient of friction between P and the slope. Well, of course, the friction equals mu r. Now, what does R equal? Well, just it's relatively easy to find. R, we can know, is coming out of the hill. That's the normal contact force, or normal reaction. Now, this here, going into here, is mg cos theta. That's what we were just looking at. Now, again, these two things are equal. I can say that R equals mg cos theta. So I can change this equation now. I can say mg sine theta equals mu times, well, these two things are equal, so I can just say mg cos theta. And you straight away realize mg is on both sides, they cancel. The cos can move over there. Mu is therefore equal to sine theta divided by cos theta. And that's great, because that equals tan theta. And I suspect that's what the answer says. So let's see. Yeah, mu equals tan theta. Good. Now I think I've got on the next slide, I've got this again. So particle B, the particle is now attached to a light inextensible string. Alright, so the same picture. Now we've got, it says, a string on it. So there's my theta again. There's my particle. And it's attached to a string, and it says it's got a pulley over the end of the slope. So this does something like this. We've got a pulley here. It just goes over this. A particle Q is attached to the other end of the string, so we've got a particle Q. This is mass M, little m. And I think this is meant to show the cap. This is meant to be an M. I don't think it's quite labelled it properly. A particle Q then is attached to the other end of the string and hangs on freely under gravity. The particle P is on the point of moving up the slope. Show that this mass equals 2m sine theta. All right, well, let's go about this. We know there's an mg sine theta coming down the hill. The hill is still going in here, mg sine cos theta, sorry, and we've still got a normal contact force, which is still going to be equal to it, R, and we've got a tension here. But the difference is they're not now equal. So we can now write that Yeah, we need basically just to write the forces up equal forces down. Notice it says on the point of moving up the slope this time. So, alright, so I've also got a friction coming down the slope. But the same idea, forces up equal forces down. So I'm going to write T equals, this tension equals mg sine theta plus now the friction. Now friction is the same as before. Now we actually found last time that it was equal to mu r. Now if you remember, we had mu equal to tan theta. Now tan came from sine over cos, so I think it might be better to write it like that. And what was r? Well, r was equal to mg cos theta. So if I put mu r in the friction here, I am going to write sine theta over cos theta times by mg cos theta. So that's the reason I wanted it tan theta as sine over cos, because the coses then disappear. And I've got mg, I've got mg sine theta twice there. I've got mg sine theta, I've got mg sine. So I've got the tension equals 2mg sine theta. Now of course that's not the only thing I know. We've got this particle over here with this particle q, and it doesn't say so. It obviously expects me to know that the mass of this one is capital M now. So just try to suss the difference between little m and that therefore creates a weight. Its weight equals mg, capital Mg, and it also has a tension pulling it up. And it's on, if this is on the point of moving, this is also on the point of moving. So for that one, I can say that T equals capital Mg. And of course, these two tensions in the rope are the same. So therefore, 2mg sine theta equals mg. The g's cancel. And m equals 2m sine theta. Yes, it does. So that's where that all comes from, 2m sine theta. So it took a long time to get there, but after going through that, we have got the right result. Okay. Example number 2 then. A block of mass 2 kilograms is being pulled up a rough slope. Or notice it's being pulled up a rough slope at an angle of 30 degrees as well. So we're going to have to resolve that and resolve this. So what's a block of mass? This is 2 kilograms. So I reckon this is mg, that's 2 times 9.8 times sine 20. So I might as well type that in. 2 times 9.8 times sine 20. Make sure you're in degrees. I get 6.704. Now it's not the only thing that's acting in that direction, because it does also say, by the way, it's being pulled up the slope, so there must be a friction coming down here as well, but I'll worry about that in a bit. What else is, well, we've resolved the weight from this 2 kilogram mass going down, so there's, by definition, there's also going perpendicular to the slope, into the slope. We've got 2 times the 9.8 times cos of 20. So let's type that in. 2 times 9.8 times cos 20. I get an 18. This is equal to 18.418. Now normally that weight into the slope is equal to the normal contact force, the normal reaction, the R. But in this case it's not, and that's because we've got this T slope which is pulling this block slightly off the slope. So we have to resolve it, and when we resolve it we get two competing forces. One going this way, which is T cos 30. Actually I think they tell me the T, it's 18. So I'm going to write 18 cos 30. T equals 18, and 18 cos 30, 18 times cos 30 is 15.588, and going this way is well, it's 18 sine 30, and the good thing about that, sine 30 is a half, so even I can work that out. That's 9. Are there any other forces? I don't think there are, I think that's it. But now at long last I can work out what this R is. So R plus the 9, basically they are equal to the kind of, in this direction must equal this direction, equals the 18.418. And so I think R equals 9.418 newtons. Now I know R, I can work out F. F is always equal to mu R. if it's unless it's not moving, then you've got to be a bit more careful. But this is on the point of moving, so that's okay. And what have I got? Mu is 0.4. I've just found R to be this figure here, 9.418. So what's that make it? Oh, times it, 0.4 times 9.418. By the time that in right, I think so. 3.7 and a bit. 3.7672, which is probably a bit more accurate than I want, but that'll do for now. So that's my F. I know this. I think I'm in the point of being able to do F equals MA. F equals MA because it's on. Is it on the point of moving, or is it? No, it is actually moving. It's moving up. So there is an acceleration, which is what I want. Yes, all right. So F equals MA. Now there's three forces acting in this direction. This is the direction in which it's accelerating. So we just got to say the positive one, which is the 15.588, minus the two that are slowing it down. That's the weight in the direction of travel, 6.704, minus the friction, which we just calculated. So notice I'm just doing these, I'm subtracting them, minus the 3.7672 is equal to the mass, which is 2 times the acceleration. And yeah, I think that will give me what I need. So let's do this. 15.588 minus that 6.704 minus the 3.7672, and I get 5 and a bit. So 2a equals 5.1168. So when I divide that by 2, I should get 2.56. Well, this will be interesting to see if that's the answer. We did quite a lot of work to get it. Hopefully it's vaguely right. 2.56, there you go. Meters per second squared. We've got, I think, a bit more to do on this. Now, remember the contact force. We've started thinking about the contact force already. We've already seen that there are two types of contact force. The resultant of this is called simply the contact force or the total contact force. In other words, if I draw a picture, there's my friction, there's my weight, my R, sorry, and these two combined, this is what we were seeing last time. And it's made more complicated now because we're on a slope. So the actual mass behind it is the same, but it's made more complicated because it's on a slope. And the R, effectively, we resolve one force, which I'll do, say, there. That's my R. And rather than drawing it down here, my friction I'm going to draw up here. One force followed by another gives me an overall force, which is the contact force there. And I suppose the key here is that we can use Pythagoras. C squared equals the R squared plus the friction squared. Or put a different way, C is the square root of R squared plus F squared. So once you know these two, you can get the contact force by doing a bit of Pythagoras. I've written that here. And what's the question say? We've got a question. Here's a question. A block of weight, 20 newtons. Notice they give me the weight, not the mass. So that equals mg, I suppose. And I probably will need the mass. So just bear that in mind. That equals the mass times 9.8. And that will give me the m later on. And I'm not going to get a chance to do all this question. I'm just going to set out what we're hoping to do. What's it got? It rests on a plane. Now rest implies it's not moving. That means up equals down, I suppose. Left equals right. So we can resolve this way. So this will be mg. Well, they've already done that bit. 20 cos 30 going this way. And we can also have 20 sine 30 going this way. Obviously we can calculate those. We'll have an r going up here. So this on the face of it is very similar to what we had before. It rests on the plane. This one, apart from this one, it's trying to, I think, there's no force pulling it up. No, there is a force pulling it up, isn't it? So therefore the friction is probably there. You just got to suss that, which one's bigger. Yeah, look, 20 sine 30 is equal to 10. So overall, as long as 14 cos 15 is bigger, and I just did a quick check and it is. So look, this is getting quite complicated. We're going to have to resolve this two directions, and eventually then we'll have some chance to do some other work. Good luck.